Namaste, Khushro Bitio. Today's topic is power. Power in size reduction and consumption of power is very important aspect of the size reduction. So how the size reduction takes place? We apply the forces on the solid particles, and by the application of those forces, that may be of any type of force, as I discussed in my previous lecture, the solid particles are distorted and strained, and by applying little bit additional forces, the stress particles are distorted again their ultimate strength, and what happens? They breaks, and the new surface is generated, and now the energy which is left after creating the new surfaces is turned up, comes up as the amount of heat, and it is not possible to exactly calculating the power consumed for developing new surfaces or in the size reduction, but there are several empirical theories available, and on the basis of that we can definitely tell us about the power consumption. And these theories, there are three theories. One is the Rittinger's, one is the Kick's law, one is the Bond's law, or you would better understand like this. One is the Kick's law and the Bond's law and the Rittinger's law. And the basic principle of these empirical relationships, these empirical theories is, they are based on a fact that the energy required to produce a unit change, a change dl in a particle of typical dimension L is a power function of the L. And we can say that dE over dL is equal to KL to the power N, where D is the differential energy required, means this is the energy required to bring a change which is equal to dL. So dL, to bring a change of dL, we need a energy dE, and that is a function of L, and L is the is the length dimension, and here K and N are the constant. So all this theory revolves around this dE over dL is equal to KL to the power N. And first is the Kick's, and Kick's law. According to Kick, the value of the N is equal to -1, and this K is equal to KK. It means Kick's constant into FC, and FC is nothing but the crushing strength. So according to Kick's law, this energy required will be, E is equal to KKFC log epsilon E L1 over L2. Means here N is equal to -1, and K, as I told, is equal to KKFC. And K is the Kick's constant and FC is the crushing strength. So that's what the Kicks want to say. Whereas Rittinger's came and he said, no, it is not the length. The value of N is equal to -2, and K is equal to KRF and KRFC. So according to Rittinger's theory, that energy consumed in combination or size reduction is proportional to the new surfaces produced, and Kick said that is equal to the new dimensions produced. So that's how that there's a difference between Kick's and Rittinger's law. In Kick's law, again understand n value of N is equal to -1, and in Rittinger's theory, value of N is equal to -2, where K, the constant, is equal to the KKFC, and here the constant K is equal to KRFC, where KR is called Rittinger's constant and FC is called the crushing strength. So that is the difference between Kick's theory and Rittinger's theory. Then comes the Bond's theory. According to Bond, which is a third theory of combination, states it very clearly says that the energy required is proportional to the length of crack initiating breakage, and N is equal to -3 over 2. So उन्होंने N का जो value बताया वो -3 over 2 बना, and this is the equation. E is equal to EI 100 over L2 power half 1 minus 1 over Q power half. So this is the Bond's theory. So these three empirical theories: Kick's law, Rittinger's theory, Bond's theory, where the values of N is different, the values of K is different. According, one is saying length, one is saying area, and one is again saying that length, but they have differed the values of the constant N. And N is the constant and K is the constant, as I told in the beginning. So these are the three theories, and what actually the bottom line of this, the conclusion is this, that Kick's law very well apply in calculating the power consumption for the coarse particles, where I'm breaking it into the coarser particles. Rittinger's theory is very well applicable to the fine particles when I'm breaking that bigger particle to fine particles, and Bohn's theory is applicable to intermediate size particles. So इस तरह से by this way these three theories are applicable to coarser particle, to finer particle, and intermediate. Again, for coarser particle, Kick's law; for finer particle, Rittinger's law; and for intermediate between coarse and fine, Bohn's theory is applicable. So these are three empirical theories which explain the power consumption in the size reduction. So that was about it, and it is a topic on which you have to emphasize a lot, and on which you have to concentrate. But the formula is pretty simple. Again, I'm telling you, dE over dL is equal to KL to the power n. In case of kick, it says n is equal to -1 and k is equal to KKFC. In case of Rittinger's theory, it says n is equal to -2, k is equal to KRFC. And in case of Bohn's theory, it says n values is -3/2. And that's all. So, and I have already told that where they applies as per the particle size. Thank you very much. If you have any question, you can write it in my comment box and I will answer that accordingly.